this unit is not that it's difficult. It's that there are three main variables that we're going to be talking about. And so you just have to make sure that you recognize what the question is asking. So for number one, it's asking you what it means if the sign of enthalpy, which is delta H, is negative. So we talked about delta H in unit 2 when we did thermochemistry. All right, thermochem was all about heat, about delta H. And so we're going to be bringing delta H back in to this unit. So if delta H is negative, that means that heat exited the system. And so that means that it's exothermic. So if delta H is negative, that means it's an exothermic process. The only thing that delta H tells us is whether a reaction or a process is exothermic or endothermic. For number 2, this was right out of the notes. The two driving forces of any reaction, so the two variables that will drive any reaction is enthalpy, which is delta H, and entropy, which is delta S. So those are two of the three variables that we'll be looking at. Enthalpy, delta H, that deals with heat. Entropy, which is delta S, deals with disorder. So we're going to be talking more about disorder today. For number 3, in nature. So in nature, that just means on its own, reactions move toward a high entropy. So in place of entropy, for some people, it helps to write the word disorder. So when a question is asking about entropy or about delta S, it helps them to think about it in terms of disorder. The higher your value of delta S, the higher your disorder. The lower your value of delta S, the lower your disorder, or the more order. So in nature, reactions move toward high entropy and low enthalpy or energy. So on its own, nature tends to become more disordered and wants lower energy. So over time, something tends to become more disordered with low energy. So when we think about low energy, we're thinking about a negative delta H. High entropy means positive delta S. So nature likes when there's a positive delta S, high disorder, and a negative delta H, so exothermic reactions. And then number 4, the following equation represents the change that takes place during fermentation of glucose to ethanol. And you're given the balanced equation. It's asking, is delta S positive or negative, and explain. So again, in place of delta S, think about it in terms of disorder. When you're given a balanced equation, compare your reactants to your products. So our reactant is a solid. Our products are 2 liquid molecules and 2 gas molecules. So you're thinking from reactants to products, are we going to more disorder or less disorder? Disorder is about the motion. In a solid, the molecules are fairly close together. So in a solid, you have your molecules close together, nice and ordered. And then it forms 2 liquids and 2 gases. So now you have some molecules that are moving a little bit, and you have some molecules that are moving a lot. Because gases have high disorder. So if you're going from more order to more disorder, we would expect delta S to be positive. So the more disorder, the higher your value of delta S. The more positive the delta S. So our reasoning, right, our explanation, we can say because disorder increases. So the more disorder, the higher the entropy, the more positive your value of delta S. S represents entropy, which we think about in terms of disorder. So we'll talk more about delta S and delta H in some of the practice questions today. So you can put your do now sheet away, get out your notes. So before we get into any of the practice, I want to answer some of the questions from both of the videos, so 9.1 and 9.2. The first was about what it means for something to be spontaneous. So on this slide, I just put the summary of the 3 laws of thermodynamics. No, you do not need to know which law is which. We're just going to take these and we're going to apply them to the math that we do. So I'm not going to ask you what is the first law, what is the second law, what is the third law. I'm not going to ask that. But going along with a spontaneous process. So something is spontaneous if it happens on its own. So if I have a marker and I hold the marker up here, if I let it go, it's going to fall. It's going to fall on its own. That's a spontaneous process. All right, if I let this go, it's not going to go up to the ceiling. That's not spontaneous. Spontaneous is if I let this go, it falls to the ground. If you have an ice cube, all right, you put an ice cube on your desk, it melts on its own. That's spontaneous. So if you have something that happens on its own, that's a spontaneous process. If it doesn't happen on its own, it's not spontaneous. And we'll talk about how to make something spontaneous later in the week. When we think about entropy, in order for something to have entropy, it needs to be moving. So the third law of thermodynamics says that if we're at absolute zero is the coldest possible temperature that we can reach. It's 0 Kelvin. All motion stops. If there is no motion, there is no disorder. Even if there's a little bit of movement, solids have entropy because solids have a little bit of movement. But once we get to 0 Kelvin, all motion stops, so there's no disorder. Talking a little bit more about disorder. A lot of this is out of your notes. I just wanted to put everything onto one slide. So entropy, disorder, increases as your molecules move more. The more your molecules move, or the more space that they can move, right? The more that the molecules are dispersed, the more entropy. So you'll notice here I actually added in aqueous. Gases have the most disorder. Solids have the least. So solids are very ordered. And you have this in your notes. You have some other pictures for entropy as well, where you have the solid is nice and ordered. Gas is very disordered. As we think about entropy, I put this last bullet point in italics down here at the bottom because I know that mastering asks some questions about entropy and it relates it to volume of a gas. So when the gas, any gas, we talk about helium. If you have helium in a small container, the molecules can only move in that small volume. It has a certain entropy, has a certain amount of disorder. If I increase the volume, there is now more space for the molecules to move. They are more dispersed. They're more spread out. That is a higher entropy. So the larger the volume, the higher your entropy. So that means higher volume means lower pressure. So always relate, if you're comparing two gases, always compare it to the volume. The larger the volume, the greater the entropy. Entropy also increases if you form gases, because gases have very high entropy. If you form a liquid or a solution from solids, that increases entropy. If you increase the number of gas molecules, so you go from 2 moles of gas to 4 moles of gas. Well, going from 2 gases to 4 gases, you're creating more disorder. That increases entropy as well. And down here, I just put the same thing that was in the do now. Nature wants low energy, so an exothermic reaction, and high disorder. So nature likes disorder. So the higher the disorder, right, the more likely that will happen. So as we think about putting some calculations to entropy, so the last slide just kind of focused on it conceptually. We can calculate entropy in a very similar way that we calculated enthalpy in thermochem. This equation is on your equation sheet. So on your equation sheet on the back, at the bottom, in the bottom left corner is the thermodynamics and electrochem block of equations. So we used Q equals MC delta T when we were doing thermochemistry and we were talking about heat. And we use this delta H equals the heat of formation of products minus the heat of formation of reactants. Well, now we're going to also use this equation that looks very similar, except instead of delta H, it's delta S. And so if we know the molar entropies of the products and the molar entropies of reactants, we can actually solve for the overall entropy of reaction. This is where Appendix C is useful. Now, all of the practice questions that I give you in the notes today are actual practice AP questions. So they give you the entropies in the question, but mastering the examples that were done, you were not given, you weren't given the entropies, and so you had to find them in Appendix C. On tests and quizzes, you'll be given those. But notice the N and the M, those are the coefficients, so make sure you take the coefficients into account. So we just add up all of the entropies of the products, all of the entropies of reactants, and we subtract them. So what we're going to do is we're just going to get into 3 practice questions. We're going to do the first one together, and then I'm going to have you work on 2 of them with your partner, right, or a small group. So I put some practice questions at the very end of the notes. So this is on page 11 of the notes. And I put these questions in here because these are from College Board. These are practice questions from College Board. So I wanted to not only give examples that show how to do the math, but also applying it to practice AP questions. So this says at 1 atm, a sample of ice is heated to liquid water and then to water vapor. The heating curve is shown in the graph above. Predict the signs for the changes in enthalpy and entropy for the process corresponding to segment X going from left to right and justify your answer. So this is going to have us look at a heating curve. So we're going to review heating curves as well because it's been a little bit since we've looked at this. But what this question is asking us to do is to predict the signs for enthalpy and entropy. So enthalpy is delta H. So we have to remember what each variable represents as well. Enthalpy is delta H. The only thing that delta H tells us is whether a process is exo or endothermic. And it wants us to look at entropy as well. Entropy is delta S. That tells us, is it becoming more disordered or less disordered? So before we look at what these signs would be, I want to review this heating curve. So as we look at the heating curve, our focus is from here to here on the heating curve. So we're looking at what is happening in segment X. But I want to look at what's happening along the rest of the heating curve as well, just to review this a little bit. So here it says a sample of ice is heated. So that means that down here at negative 50 degrees Celsius, we're starting with ice. So we're dealing with water here, which makes sense because notice that our plateaus are at 0 and 100 degrees Celsius. So from negative 50 up to 0, notice the line has a slope. When there's a slope, that means you're changing temperature. So from negative 50 to 0, all we're doing is we're heating the ice. We're increasing the temperature, we're speeding up the molecules. As soon as we hit 0, the line plateaus. A plateau represents a phase change. And so here, if we have a phase change, we have ice, which is the solid, turning into a liquid. A plateau represents a phase change. Well, if I have a solid, I have an ice cube. and I let it turn into a liquid, what phase change is that? What's happening to the ice cube? It's melting. So at 0 degrees Celsius, the ice cube is melting into liquid water. Then from 0 all the way up to 100, right? Now we have liquid. So here we're heating the liquid. When you have a change in temperature, all of the heat that is going in is being used to heat up the substance. It's being used to speed up the molecules. Then we get here, right? We've heated up the liquid. And because we're at a plateau, that means it's a phase change. So it's going to go from liquid to gas. Well, think about if you have liquid water turning into gas, what phase change is that? Right, evaporation or boiling, right? Either one works. So segment X is focusing on the evaporation or the boiling of water. And then after, we just have a gas that we're heating up. So when we think about boiling or evaporation, delta H is focused on the heat. It's focused on the energy. We have to think about, does this require energy or is energy released? So to go from liquid to gas, we have to overcome the intermolecular forces. So to go from liquid to gas, we have to overcome the intermolecular forces. Those are hydrogen bonds. To overcome hydrogen bonds requires energy. Energy has to go into the system. Well, if energy has to go into the system, what kind of process would that be? It goes into endothermic. So if it's endothermic, the positive delta H. So it says to predict the sign. So it's going to be a positive delta H. And it says to justify your answer. So I'll just say because boiling requires heat to overcome IMFs. If we were going the other way, right, if the gas was turning into a liquid, that would be exothermic because the intermolecular forces are forming. Forming something releases energy. And then for entropy, we're just thinking about the disorder. So we're going from a liquid to a gas. We just look at the states of matter. Liquid, the molecules are close together, essentially moving in place. Gas, the molecules are all over the place. Gas has more disorder than liquids. So if gas has more disorder, that means we have a positive delta S. And I'll say because a gas has more disorder, or we could say the gas molecules are more dispersed, they're more spread out than a liquid. So that was just looking at predicting the signs. This was part of a free response question, where you're just predicting the signs for each. Enthalpy, delta H, is exo or endothermic. Entropy, delta S, is more disorder or more order. So that's what you're looking for when you're predicting the signs. So the next practice question. We'll kind of set up, and then I'll have you work through it with those around you. So this was a multiple choice question. We're going to try to do this without a calculator. All right, we're going to start practicing multiple choice questions without a calculator. And you're going to see that this question can be done without a calculator. And it's not going to need a calculator to work through it. You just have to do some of the math in your head. So the reaction between lead-2 nitrate and potassium iodide is represented by the equation above. The table below provides delta S values for reactants and products. So this is where you don't need Appendix C because they give you the values. Which of the following is the approximate delta S for the reaction? So when you're trying to solve, we know that we're solving here because it's asking us for a number. Look at what you're given, and if needed, look at your equation sheet. So we're given delta S values for reactants and products. We're trying to find delta S for the overall reaction. Well, if I look at my equation sheet, I see that we have this equation. So the overall entropy of the reaction is equal to the sum of the entropies of the products minus the sum of the entropies of reactants. We are trying to find the overall entropy of reaction. Well, remember, here are our products. Here are the reactants. Don't forget to take into account the coefficients. So if we look at this, the products, here's my products. So I have PDI2. Look in the table, it's 175. Plus, I need to add up all of the products. 2 times potassium nitrate, which is 150. So here's all of my products, minus, add up all of your reactants. So lead-2 nitrate is 250. 2 times potassium iodide, 2 times 125. You can do this without a calculator. You don't have to do it all at once, but you can do this without a calculator. I'll just say, okay, I'm going to leave 175 alone. What's 2 times 150? 300. And then I'm going to leave 250 alone. 2 times 125 is 250. And then if I look at the rest of this, so 175 plus 300 is 475 minus 500. So you can do it without a calculator. 475 minus 500. So I see it's going to be negative. And then it's just actually doing that subtraction. Gives us negative 25. And our entropy units, it looks a little bit different than delta H. Usually we give kilojoules. Entropy is joules per Kelvin, which they gave us the units. We just have to make sure we pay attention. So I want to have you guys try this with people sitting next to you. So this was a free response question. So you can use your calculator. Right? There's no answer choices, so it's not multiple choice. So this has 2 parts. Part A, predict the sign of delta S for this reaction. So they give you the reaction up here. They give you the reaction up at the top. And part A just wants you to predict the sign and then justify your answer. So is delta S going to be positive or negative? And just say why. Delta S is entropy. Is it becoming more disordered or less disordered? And then for part B, using the information in the table, calculate the value of delta S for the reaction. So here are your delta S values for each individual substance. Figure out what delta S is for the reaction. All right, so work through that with person next to you, or if you want to try it on your own. Answer parts A and B. So I put the answers up here. The justification for part A might look a little bit different. Some people said it becomes more ordered. Some people said it becomes less disordered. College Board just said that you have a gas converted to a solid. So you can have different things for the justifications. If you talked about it in terms of disorder or more ordered, that's fine. But delta S will be negative. You're going from two solids and a gas. A gas is very disordered. And you're converting to just two solid molecules. Solids are extremely ordered. So delta S will be negative. For part B, you're using the equation that we used in the last practice question. Just don't forget to multiply by the coefficients. And so you get negative 181.1. And you could have either had joules per Kelvin or joules per Kelvin times mole of reaction, because it wanted for the entire reaction. Typically, we see entropy just given in joules per Kelvin, which is fine. But the unit does look a little bit different. So again, by multiplying by the coefficients, it actually cancels out that per mole at the bottom. And so you get joules per Kelvin. And if you take a look, it was negative, which matched up with the prediction in part A. So on test quizzes, AP test, they give you your values of delta S to plug in if you need to use this equation. Mastering will have you use Appendix C just because, and it'll say use Appendix C for the values. So you have to find those values on there. Any questions on any of the three practice problems? All right, so if not, for the rest of class, you have about 7 minutes left in this period. You're gonna have some time to focus on the videos. So I kind of put it in this order just to split up watching the videos. So you can watch 9.3. Both of these went up in classroom this morning. Video 9.3 is about 5 minutes. And so what I told first period is that you can watch 9.3, right? Take your notes for 9.3, work on mastering, and then you can watch 9.4, right? If you want to spend the last 10 minutes of class watching it, or you're like, I'll just watch 9.4 tonight,